guys, and today we are talking about the limits. And before we talk about some questions and definitions about limits, we first talk about a story. This is a wooden stick, and if a man cut half of its length every day, what will be remained? In the first day, we have one half of its original length remained. And in the second day, we have 1/2 times 1/2 equals to 1/4 of its original length remained. And in the third day, we have 1/2 times 1/2 times 1/2 that equals to 1/8 of its original length remained. And what about the nth day? Actually, in the nth day, we have 1/2 the power of n remained, and that number is extremely small, that is close to 0. Another story is the following picture. This is a hexagon that is inscribed in a circle. Then we add a triangle at each side of the hexagon, just like the following picture. The hexagon turns into a dodecagon. According to the graph, we can easily get the area of the dodecagon is smaller than the area of the circle. Then we can get the following equation, that is, the circle's area is bigger than the 3 triangles plus the area of the hexagon. And instead of adding the triangles, we add the rectangles, and we can get the following graphs. We can see that the graph is bigger than the area of the circle, and we can get the following equations, that is, the area of the circle is smaller than the 3 triangles plus the area of the hexagon. As a result, we can get the following equations, that is, the circle's area is bigger than the area of the 6 triangles plus the area of the hexagon, and is smaller than the 6 triangles area plus the area of the hexagon. In addition, we can further turn the dodecagon into the 24gon by adding more triangles. Then, the 24gon can turn into 48gon. As the size of the polygon increases, the area of the polygon gets close to the area of the circle. By this method, we can calculate the approximate value for pi. For example, we can turn the 96gon into 192gon. We can get the following equations. That is, the pi's value is between the 3.14102 and 3.142704. So, the idea of limit is not really anything new. As these two examples has shown, how to find a limit is just like the definition of approach. We could say it is a matter of assigning fancy notation to the intuitive idea of one value just get closer to another.
Let's see a
and this is a relative question.
First, using the following 3 graphs, what is the limit of each function when x approaches to 1?
Some students may think that the limits of gx will be 1 when x approaches to 1, while
fx doesn't have a limit.
Some students may think that there is no value existing in a and b. But the correct answer is that
all 3 functions have the same limit value when x approaches to 1, that is 2.
So how do we solve the
problem like this? First, let's look at the definition of limits.
The above graph shows the definition of limit provided by the textbook, which is extremely tedious and abstract. According to my understanding of the limit, for a function, the limit is just when the x approaches to a value, what will the y value be? The value of y is just the limit itself. Let's look back to these 3 graphs again. You can see that when x approaches to 1, all 3 functions have a y value that approaches to 2. But some students may argue that when you see the graph of fx, when x approaches to 1, the y value doesn't exist. And for gx, when x approaches to 1, the y value equals to 1 instead of the 2. But when you see the graph of these 3 functions, you can see that the graph will naturally and smoothly across the point 1, 2 for all 3 functions. So actually the limit of these 3 functions are all 2.
So actually, the limit of a function doesn't need that point exist on the function. So most of the time you can see the problem like this.
To solve this problem, we can just simply put the x value into the function. When we plug the x value, the function turns into 9 times -1, and the answer is -9. So the limit of this function when x approaches to 3 is just -9. So you just need to plug in the value and you can get the final limit. But sometimes we usually get a graph like this, and when x approaches to 1, the limit of the function doesn't exist. From the perspective of the definition, we can see that the graph cannot get through a certain point smoothly and naturally when x approaches to 1. We can apply to a new solution to deal with this problem: two-sided limit. Two-sided limit includes two parts: right-sided limit and the left-sided limit. Right-sided limit, in the simple word, is that when you see the graph from the right to the left, when x approaches to a certain value, what is the y value is. Left-sided limit is that when you see the graph from left to the right, when x approaches to a certain value, what the value of y is. For example, using the above-mentioned graph, the right-sided limit of the function when x approaches to 1 is 4, while the left-sided limit is 3. The right-sided limit is not equal to the left-sided limit, so the limit is not exist at this point. Remember, when the right-sided limit and the left-sided limit is not equal, the limit is not exist. And there are several theorems of the limit.
The first
one is the properties of the limit.
The properties are very easy to understand
and convenient to use. The point is
when
that
we solve the
when we solve the problem, we need to quickly understand whether we need to apply which properties or not. Remember the properties, remember the properties, and remember the properties. And this is one of the most important theorem in the limit. Just like its title, the sandwich theorem, it means to squeeze the two sides to approach the middle one. The most easy way to learn the theorem is to do the questions.
So how do we apply the sandwich theorem? Let's look at an example. So how do we solve this problem? We know that the values of the sine function lie between -1 and 1, so it follows that because when x approaches to 0, the negative x squared and x squared approaches to 0. So according to the sandwich theorem, it gives that when x approaches to 0, the function x squared times sine of 1 over x equals to 0. Now we are primarily dealing with the limit of a specific value of x. What if x approaches to infinity? This is my favorite part of the limit, because once you get the method, all the questions will be as easy as the problem in year 1. Let's look at an example. The yellow line is the graph of x equals to 1 over x squared, the same function as the first problem has depicted.
As the graph shows, when the x approaches to the positive infinity, the value of y approaches to 0. Let's put the x value into the equation. The equation will become as 1 divided by an infinite large number. The final will be extremely small that can be treated as 0. So actually the limit of this function is 0. And another example is the two graphs actually looks very differently in this interval. And the first function is y equals to 5 times x the power of 3 and plus 7 times x squared minus 89 over x squared, and second function is 5x. And
the two graphs
actually
overlap each other when x approaches to infinity.
The two graphs actually overlap each other.
X value as infinity,
this is
compared to 5 times x to the power of the 3,
compared to
5x squared minus 88 is too small to write. So the equation can be written as 5 times x to the power of 3 divided by x squared, which equals to 5x. In another way, when you see the function like this, fx divided by gx, just look at the highest order term in each function. Actually, by calculating the limit of x approaches to infinity, we can get the horizontal asymptote
of the function.
This is a problem from the AP Calculus exam, and the question wants a horizontal asymptote of this function. So how do we solve this problem? Let's find the limit of this function when x approaches to the positive infinity and the negative infinity. So compared to the x squared, the negative one is extremely small that can be ignored. So the equation can be written as this. And when we plug in the positive infinity and the negative infinity, the problem can be written as this. And the final answer is the positive 2 and the negative 2. So the horizontal asymptote of this function is just y equals to positive 2 and negative 2. So the problem is solved. And following is some tips that I want to give you about the AP Calculus exam. Actually, the AP Calculus exam is very simple, and all you need to do is to remember the properties of the limit and the definition of the limit, and make sure that you have to do enough the practice. Don't be nervous. It's very easy as long as you have prepared. That's all.